seen this a little bit already because I was too excited about limits to not show you. But this is the official notation. We write LIM for limit, and we would read this, that the limit as x gets close to a, or x approaches a, of f of x is equal to L. So f of x, you could put any function in there, and then you're imagining if we got close to that value of a, which could be any number, what is it equal to? And a lot of limits are really, really easy. Okay? So the limit as x gets close to 5 of 3x minus 8 is equal to 7, because if you plug in 5, 3 times 5 is 15, minus 8 is 7. And if you plugged in something close to 5, you'd probably be close to 7. In fact, if you have a graph like 3x minus 8, and limits are a lot about thinking what's happening graphically really helps you see it. But if I drew 3x minus 8, you would have a y-intercept of minus 8, a slope of 3, and we have the point 5, 7 on that line. What a limit is really asking you is if you were getting close to 5 this way and close to 5 this way, where would you be on the graph? So if I was coming from the left-hand side close to 5, can you see that you would be traveling along here and going this way towards that point? And from the right-hand side, you'd be traveling down here from the top and going this way. And if both of those directions end up at the same place, then that would be the limit. Now, if you have a graph that you can draw, and we call, there's all sorts of graphs you can draw, but if you have a graph that you can draw the whole graph without lifting up your pen or pencil, whatever you're using, we would call that kind of graph continuous, because it doesn't break up. Like a graph with an asymptote has a place where it's discontinuous, because you'd actually have to lift your pencil up, start again in another spot, and draw. So if a graph is continuous like this, that means the limit will always be just what you plug in. Does that make sense? Because if you can approach it from the left side and the right side, and it's obviously going to go to the same point, because you haven't lifted up your pen and gone somewhere else, then we could just plug that number in. So here, what's the limit as x goes to 0 of this one? It's going to be minus 8. As soon as you can plug in a value, you can figure out the limit. But there might be some functions, right? Something like this. It has definitely is discontinuous. If I was coming from this side, it would approach this number, this y value, but from this side, it would approach a different y value. Then we say the limit doesn't exist. Because as you're getting close to whatever the x value is there, the left side and the right side are different.
Sorry for the interruption. Grade 9 students, French immersion students of grade 9, head down to the theater. English students of grade 9, please make your way down to the gym. Again, that's French immersion students for grade 9, please make your way down to the theater. English students for grade 9, make your way down to the gym, please.
All right, so this is this idea of continuous functions. A function is continuous. This is not the official definition. If you pull out your math dictionaries, right? Let's see. If you pull out your math dictionary, it doesn't have in there that you can draw it without lifting your paper. Does everybody have an official math dictionary? So if we pull out the, wow, I did that. That was awful. Your binder survived?
Yes.
Okay. If we pull out the official math dictionary, there we go, and look up continuous. This is a pretty thick dictionary. It's just math stuff, right? Oh my goodness. The definition in here for continuous function is a page and a half. A function for which a small change in the independent variable causes only a small change and not a sudden jump in the dependent variable. That is more official. However, I like the fact that if you can draw it without lifting your pencil, it's very intuitive as far as understanding what's happening. So all of our polynomial functions, x squared, x cubed, all of those ones would be continuous functions. And if you have a function that is continuous over the interval that you're trying to solve for, your limit is just the ability to plug it in. So those limits are kind of boring. I'm sorry. It's like almost like a grade 9 or grade 10 question when you first learned functions and said, could you plug in 2 and figure this out? The answer is yes. Right? All I'd have to do is plug in 2 for x. 2 squared minus 1. This is a very, very easy limit to figure out. Same thing here. You would just have to plug in -1. And then work through your mental math to figure out the value. So those kind of limits aren't actually very exciting because you can just plug things in and figure them out. But where we do get into exciting stuff, as I mentioned yesterday, is when we start to try to do something we're not allowed. We're not allowed to divide by 0, and that is often what happens in limits. In particular, we're going to look at 0 over 0 limits. 0 over 0 limits often have a hole in the graph. And you saw these graphs in grade 12 pre-calculus. What you found is if you were graphing, for example, right, we're going to consider the following rational function. If you tried to plug in 3, you would get 0 on the top and 0 on the bottom. And 0 is a non-permissible value. If you were graphing this from last semester, you would have stated that you have a non-permissible value that x can't equal 3, but this simplifies, and now we get just y equals x plus 3. And that's a straight line, but you still have a non-permissible value at x equals 3. So when I go to graph this, I would have this line, but I would be like, oh, wait a second. At x equals 3, I have to make a hole in that graph because 3 was not allowed. Even though it's simplified and went away, in the original equation, 3 was not allowed. So I draw this by drawing the new equation, straight line, but it now has a hole, and I can find that hole in grade 12. We took the new equation, plugged in 3, and said the value of that hole is at 3, 6. Now, thinking about the limit from a graphical
Alrighty,
perspective,
sorry for the interruption. Last call. Grade 9 students for French immersion, head to the theater. English students of grade 9, please head to the gym. This is your last call.
if we are finding the limit as x gets close to 3, we imagine getting close to 3 from the left side, and that would be, I'm on the graph going this way, and getting very close from the left side to 6. And I go from the graph from the right side, so I'm going towards 3 this way, and I'm like, oh, I'm also going close to 6. And so the closer I get to 3, the closer I'll get to 6, whether it's from the left or from the right. And so we are going to say that the limit of this function right here is equal to 6. And that's the idea of a limit, and these ones are a little bit more interesting because you can't just plug in a number right away. What we have to have is those algebra skills that we looked at yesterday to see if we can evaluate them. So the idea of a limit is we are going to try to evaluate to get rid of that non-permissible value, in a sense creating a hole graphically, and then we'll be able to evaluate it. I got ahead of myself. I've already drawn this, but we can draw it officially. What you did already on your graph. Okay. All right, good. Then we call the point at x equals 3 a discontinuity. I don't know, in grade 12, most math teachers will call that a hole because hole has 4 letters and it's really obvious and short to write. Officially, it's called a point of discontinuity. So there was one year on the exam that had a bunch of students, because the exam just said point of discontinuity, and they were like, what does this mean? Like, the whole. But, oh, and there was an announcement, yeah, I said there was an announcement last time the exams are coming back next year. Crazy. So we have to simplify, and then we can figure things out. So we'll get questions like this. Your job is to factor, to rationalize. We've got 4 questions here. Try the first one on your own. Look back in your notes if you're having trouble factoring. All right, how did your factoring go? Did you see the top as a sum of cubes? You might have had to look back at your formula, but you should have got x plus 2, x squared minus 2x plus 4. And sometimes, if they're asking you for a limit that involves factoring, and they're saying the limit as x goes to minus 2, math is bad about giving hints away. If that's going to be a whole, what do we need to cancel out? We need an x plus 2 to cancel out on the top and the bottom. And if I plug in minus 2 and the bottom is 0, which it is, and the top is 0, which it is, that's the only possibility. So in a sense, they've already told us the factor on the top and the bottom. Yours can kind of cheat because you don't have to be as good a factor when they tell you a hint like that. So now that I know that the x plus 2 is on the top and the x plus 2 is on the bottom, and those will simplify, I'm left with this as my limit. Now, notation-wise, when we're solving limit questions, we write the limit as x goes to 2 every time until we get to the point where now I'm allowed to plug in minus 2. It's It's no longer a non-permissible value in the simplified version. This would be, if you were at this point in your graph, you'd be like, I can find the hole in my graph now. So now that you plug in -2, you do not have to write that limit part anymore, because now you've started to evaluate it. But before you can plug in the -2 and evaluate it, you do have to write that limit every single time. And it simplifies nicely to be 6. Some things that you can do that will help you mathematically in any subject going forward, or in this one as well. As you're doing a question, your brain should also be going, how does this connect to the unit I've done before? Like, you graph rational functions. So this idea of having a hole in the graph. What were we left with after the hole canceled out? We were left with x squared minus 2x plus 4 over x plus 4. Could you still graph that using your skills from grade 12? What would it look like? And maybe, and some of you probably didn't even, in grade 12, some of you didn't do the ones with the diagonal asymptotes, and some of you did. This one does have a diagonal asymptote in it. Okay, next. Oh, I like this. Oh, this makes me happy. So far, I have seen 2 different techniques that are both correct for starting example 3. So once you've finished example 3, see if you can figure out what the other person's technique was that was different than yours for starting this off. And if you're stuck, call me. So that, like, when we're stuck, sometimes we just say, well, what could I do? And we try it. And sometimes you're like, oh, it actually works. And sometimes, oh, that didn't work. What else could I do? So what can you do with this h minus 3 squared? You could multiply that. See what that does. And that'll, right? That little, otherwise you did make it impossible. Method number 1. Take the limit, and we have h minus 3 squared. Don't know what to do. Well, I could multiply that out and see what happens. If I multiply that out and see what happens, I'm like, oh, my 9 and my minus 9 would go away. That just gives me h squared minus 6h on top. My goal is to get rid of the non-permissible value. So I would need to cancel out an h. So at this point, I could either factor that h out. Some people just simplify it directly, but once that h is factored out, we successfully can simplify that, leaving me with just h minus x. And when I have just h minus x, now I can evaluate. I could plug in 0. 0 minus 6 is negative 6. And we've evaluated the limit. Method number 2. As I said, some people were doing this method. This is probably the most typical, multiplying it out, simplifying things. But sometimes you can recognize this is a difference of squares. We have something squared minus 3 squared. So if I factor this like a difference of squares, it would be plus 3 minus 3. But the first thing would be h minus 3 and h minus 3. I can put that in little brackets if you like. Can you see that as a difference of squares? Something plus 3, something minus 3. And if I now simplify this one, would just become h. And this one, minus 3 minus 3, is h minus 6. And we've gotten to this step a different way. So the beauty about seeing different ways to get to the same thing, and also the frustrating thing in math, because the more math you learn, the more options you're given, and the more options you're given, the harder choice you have, because you're like, oh, should I do this or should I do this? And sometimes, like in this one, I would say they're relatively equal. Like not one doesn't necessarily give you a huge advantage over another. But there will be some cases where there's an option that is better than the other one. Makes your life easier. Having both of them available in your mind gives you options. And you can sometimes look at this question and go, oh, should I factor it as a difference of squares or should I just multiply it out? Right? If this happened to be h minus 3 to the 4 minus 9, the difference of squares might be a lot nicer. The other skill that we learned or practiced yesterday was rationalizing. And rationalizing a numerator or rationalizing a denominator is often an important skill for evaluating a limit. This one again, if I plug in 0, the top would be 0, the bottom would be 0. So because it's 0 over 0, there's a good chance this graph has a hole. I need to cancel out this x, but there doesn't seem to be any factoring that I can do on the top. So this is an example of where we look at, can I rationalize the denominator, or numerator in this case? So I'd multiply by the same thing with a plus sign because I want to use that idea of a difference of squares. And since we want to cancel out the x, it really makes sense to leave the bottom factored. Multiplying it out would just mean we'd have to factor it later again. So because we have an idea, an understanding of what we want to do, it kind of guides our math. Now, the top, I definitely want to multiply out because I want to see if I can get an x. So I multiply the top out. As a difference of squares, it would be this one, and I can put brackets around it because that's root x plus 16 times root x plus 16. When that gets squared, just the square root would go away. And then I have a plus 4 and a minus 4. That'll give me minus 16. And we can see that something really nice is going to happen on the top. The 16s are going to cancel. And we're just left with that x on the top. Once again, careful when everything simplifies on the top. That doesn't mean that it's gone completely. The fraction's gone. There's still a 1 left on the top of that fraction. And now we've changed it to something that when we look at it, I could plug in 0. 0 is no longer a non-permissible value. Plug in 0. We'll give you 1 over 8. And what we also start to do is we get more and more complicated in math, right? Like we saw in that previous example with factoring a difference of squares. It's not your typical looking difference of squares, right? We had an x minus 3 all squared minus 9. But that's the kind of thing that we want to start to see. Math is a pattern of what we're allowed to do. And you're allowed to do it with all the numbers that exist, which is an infinite amount of them. Right? It would be terrible if you had to memorize, okay, we're learning adding like terms. We have a million rules to memorize. First, x plus 2x is always 3x. And we're going to memorize x plus 3x is always 4x. But once we realize the pattern, we can remember all million rules as just one rule and apply it to all of them. That's the power of math. So when we have this idea of rationalizing a numerator or rationalizing a denominator, sometimes it can appear in more complicated situations. Like here, I have the square root of this minus, and then I have an x plus 1 instead of just minusing a single number. But we can still apply the idea of a difference of squares and rationalize this denominator instead of having to memorize a new rule. Why? If you want to check your algebra after step 1, I would leave the top not multiplied out. In fact, I would factor the top, but I would multiply out the bottom. And if you've multiplied out the bottom and subtracted everything, check that you are able to simplify the bottom correctly. which factor do we want to cancel out? We want to cancel out that x minus 2. So right now I have a minus 2x plus 4 on the bottom. I hope that you can see that there's a common factor there. Pull out that minus 2. And the reason we pull out a minus 2 instead of a positive 2 is because we want to get that x minus 2. And then we get to do what I believe is one of the most satisfying math exercises, is just canceling out factors. It just feels so good. Cancel out that x minus 2. And we have gotten rid of the one value that was causing us problems. So now we can plug in to evaluate it. Sorry, I'll put that back. So what did we discover in this question? We discovered that there is a hole at 2, negative 8. One of the things that is interesting to do is to take out, and you can download this app on your phone, it's called Desmos. Sometimes it's just interesting to see, well, what does this graph look like? So I'm going to type it in to Desmos, x squared plus 2x minus 8 divided by square root, SQRT makes a square root, and then it draws it for you. That's kind of cool. X squared plus 5 minus bracket x. Oh, I'm actually disappointed. I was hoping for a more exciting looking graph. But apparently, if we would look at Desmos, there it is. If I click on 2, it goes 2, undefined, saying that that value is a hole in our graph. Okay, so at the bottom of your page, you have homework listed. So I'd like to give you 15 minutes now, so that sort of takes up, I said, make sure you spend at least 15 minutes tonight on stuff. So you can have tonight off if you spend the next 15 minutes working on those questions. A suggestion that some students do, if they have their textbook on the questions, they use their phone and the textbook that I gave you the document link to. They take their phone out and have that for the answers. So then you're working on the questions, but you can look at the answers as you're going all the way through. If you don't have your textbook, then take out your phone and bring up the textbook on your phone